Okay, welcome everyone. I've got the important job of introducing the person who's doing the introduction. So I just thought I'd go, this is the first in kind of a series of kind of hijacking the ACFR seminar series once every couple of months, probably, to do an ARIAM specific seminar series. So we'll be joined online, hopefully by some of our ARIAM colleagues at, well, I guess maybe for those who don't know, probably everybody knows, ARIAM, the Australian Robotic Inspection and Asset Management Hub, was launched in November last year, and we've kind of been building up the team since then, and so many of you are getting to know many of our new people. We've got lead node at Sydney, QUT and ANU are the other academic nodes, and we've got around 15 industry partners. So what we're introducing is a new seminar series centered around ARIAM, which is going to involve a mixture of presentations from academic presenters within ARIAM or kind of external presenters somewhat related to ARIAM's mission, and also presentations from industry partners. So we've actually got two of our new ARIAM postdocs on the stage today. So Will Jones has very graciously accepted to take on the role of organizing this ARIAM seminar series. Some may know Will already, who has had a kind of past stint at ACFR at RTCMA, but he's back now with ARIAM working on sort of ship dry dock optimization. But he's going to take on the mantle of organizing the seminar series. So maybe now I'll hand over to Will to make the introduction of our special inaugural speaker.
Yeah, thanks very much, Ian. So yeah, as Ian said, we're going to try and run this seminar series sort of every couple of months. We've already got some speakers lined up for the end of the year, but please, if anybody sort of knows anybody who would be a kind of relevant speaker, then please do reach out. But to kick off our series, we chose nobody better than Alex. So Dr. Alex Cardaillac is a postdoc researcher in underwater computational imaging in the ARIAM Hub. He's been here since last year. He received his PhD in 2023 from the Department of Marine Technology at the Norwegian University of Science and Technology as part of the Applied Underwater Robotics Lab. And I believe today he's going to talk about his PhD research. So over to you, Alex.
So good afternoon, everyone. So thank you for the introduction. Thank you, everyone, for joining here and online. So as we already said, I'm going to be presenting today the work I've done during my PhD in Norway. So this presentation is actually based on the PhD defense, but with some simplified parts and some other that are extended. So I worked on autonomous underwater inspection using robotics. So this thesis was about underwater robotic navigation, perception for end-to-end shiphull inspection. But before we go into details about the methods and results, I would just first like to start with a definition, which is about what is end-to-end. And this is because it really defines what is the scope of this project and really what it is about. So if we look at the Cambridge Dictionary, end-to-end refers to something from the very beginning of a process to the very end, including all the stages of a process. So if we put this into context, in the context of end-to-end robotic solutions for technical inspection of infrastructures, it actually refers to the complete operation from the selection of the appropriate platform, sensors, and so on. And also it's about designing the right navigation and control solutions and how to efficiently and reliably communicate between the platforms and the surveyors. So it's really about having all the components of the solution all together. So more precisely, when it's about shiphull inspection, it's again start with the selection of the appropriate underwater vehicle and the sensors. It includes all the data collection methods and processing in order to correctly document the hull condition and the structural integrity of the hull. And similarly as before, it's also about establishing the correct communication links between all the actors during the operation. So during the autonomous agent, the surveyors and operators. And it finally ends with a way to support and really assist the surveyors for the decision making by creating reports about the condition of the hull. So very briefly, I will first talk about why do we actually need to inspect ship hulls underwater, and provide some objectives and results, and finally some conclusions with potentially future work. So for the motivation, as you might know, today there is approximately 56,000 medium and large ships that are navigating on today's world seas, and they really compose this maritime industry that has become a crucial part of the world's economy. And according to the United Nations, it's more than 80% of the global trade that rely on the ship transport. But when we refer to the shipping industry, we also refer to most of the activities that are done at seas, and that also includes the transport of people, products, or goods. And the ship owners, they are required by international regulations to perform regularly inspections. And this is because when the ships are navigating around the world, they are actually exposed to the environmental conditions of oceans, which can be very harsh to them. And over time can lead to structural degradation, such as cracks or biofouling, which really impacts the operations. And so traditionally, the inspections are done in dry docks, which take a lot of time and cost a lot of money. And so there's this need to improve this process so that it can be made more efficient and more quick. But luckily, with modern technologies, we can help reduce this downtime of the ships by automating the in-water inspection. But of course, there are a few challenges that comes with it. First, it's because it's underwater. It can be very challenging sometimes just to navigate and to account the weather and all these things. But also because there is very large variety of ships. And if we want to provide a solution that can work in practice with many different ships, we have to consider that there's not only one ship with one size and one shape. So this is important to consider, but also we want to comply with the rules and regulations from international organizations so that the solution in the end can be actually used by surveyors and class societies. So during this project, I would say the global objective was to really improve the capabilities of low-cost underwater vehicle in order to inspect autonomously the underwater outer ship hull. And for this, there are several parts that comes in play. So from the management of the mission to the low-level control of the vehicle to navigate along the hull. So for this, we can actually divide into 4 different objectives that were my main objectives during my PhD. So first, it's really about planning and control. So how can we plan efficiently the path around the ship so that we can fully inspect it? Secondly, it's about detecting the actual faults on the hull and the different ship parts that surveyors are typically looking for. The third one is about this time really providing more insights about the ship parts that we inspect. For this, we sort of try to combine the sensors that we have available, so monocular camera and a sonar. And the last one, it's really about creating this end-to-end solution that can be used in practice by the surveyor, so that it becomes possible to monitor, document, and report the hull condition. So very briefly, for this project, I use an ROV, a remotely operated vehicle. This is the Blue Eye X3 ROV that you can see on the left here. And on top of this, we have some external sensors, such as a forward-looking sonar, but also GPS that is very useful when we come back to the surface, so that we can be aligned with the global frame. But important to note is that the vehicle is actually connected to the surface unit here that actually establish the connection and the communication between the autonomous vehicle and the surveyor. And on the right, you can see the perception sensor footprints when it's facing a the ship hull. So very briefly here, I would like just to present what is a forward-looking sonar. So basically, a sonar, it works in a specific way. It emits acoustic beams with fixed vertical opening angles. And then when it measures the signal strength and the time difference between the signal emission and its reception, by measuring the time of flight, you can also estimate the target range. And because the beam has a beam former, you can also understand the horizontal flaring angle of each beam. But unfortunately, it's not possible to derive the vertical angle. So if we look at the figure on the right here, we would have multiple beams like this. And for each beam, we would have only one value for each range. So in the end, that's why we obtain 2D image that we have here on the right. Right. Also, so during this project, I was very lucky to be able to access many different harbors and ships around Europe. And this really enabled extensive testing on many different ships of different size, shape, and so on. So a few examples I was able to test, for example, in Norwegian fjords on research vessels, but also on cruise ferries of Greece or even NATO warship in Portugal. So this really made it possible to provide a solution that can work and can adapt to different ships and conditions. Right. So now, of course, the first step is to be able to localize the vehicle when it's underwater. So I'll be very brief about this because we actually use an existing framework for this called MARS, but we extended it for underwater applications by handling more sensors that are related to underwater navigation. But it's actually a very useful one because it handles measurement outliers and outages, which can occur quite often underwater with some of the sensors, but also it provides some online specific calibration of the sensors and some uncertainty measures that we will use later on. But perhaps the most important part here is how do we actually plan a path around the ship so that we can efficiently inspect it. So we have to take into account the constraints. Of course, we want to be able to visually cover the hull so that the surveyor can take note or assess it visually. But the constraints we have is that we don't know the shape of the hull prior to the operation. And also, we need to be always facing the hull and ideally at a constant distance and with a low speed so that all the images we have are consistent. So first, we actually define two types of categories, path categories. We have the transit path, which correspond to the path the vehicle has to follow from the deployment point to the ship, because we want this end-to-end inspection. So as soon as the drone is in the water, we just don't touch anything. So the idea is just to create this path so that the vehicle knows where to go to reach the ship. And the second one is the actual inspection path. So the path the vehicle has to follow to perform the inspection. So as I said, the operation starts as soon as the operator deploys the ROV and then sends the mission details, which are the location of the ship and the region of the hull to inspect. And then the ROV follows it after generating opening graph around it that we saw in the video before, and simply extract the shortest path to the start of the inspection pattern, and it follows it using line of sight guidance. But here, more importantly, is how do we actually plan the path for the inspection? So as I said, we don't know the shape of the hull. So first, we generate a lawnmower pattern, a vertical lawnmower pattern, with either horizontal slices or vertical slices, depending on the shape of the hull, and depending on what kind of inspection we want to perform. And it's designed to fit the actual desired inspection region and takes into account the camera's coverage capabilities, so that we can have some overlap, for example. But the hull is not flat, right? So we need to update this path as the vehicle is moving. So for this, there is a specific mechanism that is based on the sonar And so I will go through this figure so that you can understand how it's done. First, we have the vehicle that is on the reference path, here, red, B, and going from the left to the right. But the way it is positioned now doesn't correspond and doesn't satisfy the constraints we have, which is being at a constant distance and specific orientation relative to the hull, so that we can efficiently inspect it. So the idea is that using the sonar, we can actually see the hull locally. So then we can just, using the local information, project on what we believe is the hull. We project the vehicle on the local hull, and simply with this information, it's actually enough to just translate the path and rotate it, so that in the end we obtain this yellow dotted segment, P prime, which corresponds to our new path. But here again, you can say at some point it's not going to be facing the hull anymore. So the idea is to do this for each new measurement, so that in the end, the path that we get is actually matching the shape of the hull. So the important part here is the detection of the hull using the sonar. So remember that you have this assumption that the hull is locally flat. And because of this, we can, it becomes possible to say that we should expect an acoustic line in the sonar data. And this acoustic line should provide information about the distance to the hull and its orientation. So first, we have on the left the raw sonar data, which is a bit noisy and polar coordinates. So the first step would be to remove some of the noise and select only the relevant features, acoustic features. So for this, we use an edge detector, which enables to, at the same time, specify a bit the data and keep only the important information. And then when we transform the data in Cartesian coordinates, if you look at all the blue points, we can already see some kind of line here. And the idea is to then fit a runtime line that would then correspond to the hull. And just looking at the geometric details of this line provide us all the information we need to continue the path following system. So another example here with on the left, the sonar data, and on the right, how it looks like during the operation. So we can have the raw sonar data between Cartesian coordinates on the right, with in red all the extracted acoustic points, and the blue line is the detected hull. And you can see on the bottom is the detected estimated distance and relative heading. Right. So now, compared to the previous path, we don't want to use line of sight anymore. And that is because we want to have better control at slow speed, but also we need to be able to specify more accurately the speed along the path. And so for this, we use a maneuvering-based guidance, which is based on constant bearing linear approach, which also provides some components to compensate for some of the errors. For example, for inspection, the errors in depth and heading are especially important because we always want to have visual coverage of the hull. So I'll just quickly go through this equation so that you can understand what's the idea behind. So we want to have a desired velocity along that path, which is defined based on a speed assignment, which corresponds to the speed the vehicle should have at each specific point of the path. And the second part, but I will go into details, this specific speed assignment later. And the second part of the equation is the constant nonlinear bearing approach, which is, as you can imagine, based on the position error, because the idea is to have always the vehicle converging towards the path at the same time as it's satisfying the inspection constraints. So that's why the second part is really important, so that we ensure that the vehicle is always safely on the path. And we have factored to the error the approach speed that defines how fast the vehicle should be converging towards the path. So this speed assignment is where we actually take into account the errors, the inspection errors, and especially the errors in heading and depth. So the ratios we have here, they actually mean that as the error grows, then the vehicle will slow down. And we then have like input from the operator, which is the desired speed, which is usually about 0.5 meter per second for typical inspections. And then we have a speed modifier so that the vehicle slows down at corners, for example. Right. So now we can navigate along the shape, but we still need to monitor it and at least perform the actual inspection. So we want to provide the operators and surveyors that are part of the operation all the information they need to understand the mission progress and also monitor what has been done, potentially what part of the hull is missing. So we really want to provide output data that are relevant for the surveyors. So for this, we use only the sonar, and that is because it's very reliable sensor and work very efficiently regardless of the water gravity. So it's very convenient in this case, but it also means that we don't have, it does not generate a realistic 3D model of the hull. It's really about monitoring the inspection and having an idea of the progress. So here again, we have this assumption of the local flight surface, and we embed in this acoustic map some uncertainty estimation information so that surveyors can better understand the quality of the inspection specific areas. So the idea to create this inspection map is that for each beam of the sonar, we select only one feature and the closest one to the sonar. And by doing this, we actually minimize the reposition error. And this is because we have this flat shape assumption. Because if the surface that is in front of the sonar is flat, it means that the closest point to the sonar is likely to be on the horizontal plane related to the sonar. And therefore, if we project it again in the 3D world on this horizontal plane, then we have a minimized reposition error. But this only works because of this assumption. And so we accumulate points for each new sonar measurement, and over time we obtain a dense point cloud that we discretize as a voxel map. So here you have an example of what kind of voxel map you can get, and with, in addition, the uncertainty information. So we have two sources of uncertainty. First, the sonar, how accurately we actually are mapping the hull, which is based on estimated ground truths, because before we detected how the hull is positioned relative to the ROV. So it means that we know how the data should look like. And we can extract from this some uncertainty information. The second source is the pose of the vehicle, which is very important to consider, which is extracted from the framework I displayed before. And in the end, because we want only one value, in the end, we just apply the weighted sum. So here are some other examples. On the top row, it's on the left, it's dense point clouds from the acoustic data. And on the right, it's the voxel map. And on the top row, it's an autonomous inspection of harbor walls. And on the bottom, a small research vessel. But in practice, how does it happen? So here you have two examples of that were recorded during the operation in real time, but of course with accelerated videos. So on the left, it's the inspection of a cruise ferry in Perama shipyard in Greece. That was about 200 meters long and 6 meters deep. And as you can see here, it might be a bit difficult to see from where you are, but you can actually see the green pattern here, which is the reference lawnmower pattern. And then you can see a red line, the red segment that is moving, which corresponds to how the current path segment is translated and rotated to match the shape of the hull using the sonar. And then on the bottom right, you can actually observe the sonar data and the top right, the images. The difference between the two videos is that on the right, when this was an inspection of a decommissioned warship in a naval base, we are actually performing inspection with horizontal slices, which is more suited for that kind of ship because they don't have this curvy shape over the depth compared to cruise ferries. And so the idea is that we can perform similar inspection like this with any kind of shape of hull. So now we start to have a lot of data, but we are still missing one important part, is the actual detection of defects on the hull in the fault. And ideally, we would also want to localize these defects in faults on the different point of interest. So we also want to model a specific point of interest and detect them. But we have one issue, is that we want all the results to be scaled so that they can be used for measurements by the surveyors. And if we only use the camera, we don't have scale. But on the other hand, if we only use the sonar, we don't have realistic representation of the ship parts. So the idea is to find a way to combine both sensors, to sort of combine the best of both worlds. So first, we actually try to process in parallel both sensors. For the camera, we perform some contrast enhancement, run in snow filtering, and then we use the OrbSTAM framework, or could be any STAM framework, but in this case, we use OrbSTAM to obtain efficiently a point cloud and a pose over time. And similarly for the sonar, we first start by doing some noise filtering contrast enhancement. And again, we select only the closest features with highest intensity and one per beam. So this time we don't have the flat shape assumption, because if we inspect, for example, a propeller, well, it's not flat at all. So we have to look more closely about how is the sonar position relative to the camera, so that we can have some kind of point correspondence between the visual points and the acoustic points. So if we look from the top-down view, we can see that both the sonar and the camera are horizontally aligned. But from a side view, we can see that the sonar is slightly above the camera, which means that for the same feature, the feature will have the same horizontal angle relative to both sensors, but a different vertical angle relative to both sensors. So we have to take this into account. So I just put back this figure here so that you can remember what's the geometry of the sonar. So the idea is that we will have, because we select only the closest feature per beam, we will have only one feature per beam here. And we start by localizing it on what's called the zero elevation plane here. And the idea will be to try to restore the elevation so that we know where it is on the beam. So for this, and because we know the sensor calibration, how the sonar is positioned relative to the camera, we can actually project the sonar beams, the acoustic beams on the camera image. So for example, if we look at this sonar image, then each point you see here correspond to segments you see on this image. And there are segments because, again, we don't know the elevation angle. So they could be anywhere on a circle path that is projected on this image. And the idea is to try to find where is the point on this specific segment of the image. And because the sonar is located on top of the camera, it means that the closer the target, the higher the projected beam is in the image. So intuitively, if we look at the pillar here, the closest points to us, so the left part of the pillar, are actually higher than the points that are at the back of the pillar, because it is further away. Similarly for the back of the pool and the wood object. So how do we do this camera sonar correspondence? First, because we selected only the closest acoustic points, we do the same operation with all the visual points we have. So we take all the 3D point of the point cloud, and the closest to the closest points of this point cloud, we only keep the 2D correspondences that are located on the segment. And then simply by checking all the distances, we can have matches between the acoustic point and visual points. And, and this is what is represented here in this figure. For example, you can see the sonar beam here in purple, and you would find a green feature, which is visual feature that lies on the same part of the image. Then we have a match. So for each match, we obtain a scale so that we can rescale the points in the 3D world. And as we accumulate these matches in these ratios, we actually build the data sets that we found out to be following a normal distribution. And because of this, it becomes easy to do some basic statistical operation on it to remove outliers, so on. So we still need, in the end, to obtain one global ratio to restore the scale of the point cloud and the trajectory. So for this, we use the maximum likelihood estimation, which is known to be robust as the data grow larger. So, and because we have the data set that accumulates for each new frame, we in the end obtain a very large set of data. And so you can see on the top right, we did some comparisons using the MLE, so our method, compared to only using the median or the mean value. And as you can see, it's that the MLE is super stable in comparison and also converges quite fast to 1, which means that we reach the right scale ratio. And we also did some comparison when we use multiple beams of the sonar in only one beam, the central one. And similarly, there are stability issues with the single beam. So with this global value that we have in the end, we can just apply it to Obstam point cloud trajectory so that we obtain a correct scale value that the operator can use to perform measurements or simply for the safety of the operation. So we tested this and compared this to multiple framework, SLAM-based framework, such as visual inertial SLAM, but also monocular SLAM and DVL-based data reckoning. And we could see that for most of the metrics, using the sonar actually improved quite a lot the results. So here are just two examples of what kind of models we can get out of it. So on the first row, it's not a ship, it's actually the inspection of the big loop module, which is an underwater asset for the oil and gas industry. And on the bottom, it's the inspection of a propeller of a research vessel. And so not only this helped obtaining more dense point cloud, but also for the second step, which is the reconstruction, it actually provides more robust and accurate results. So that's great. We have models. We are now able to model all the different points of interest, but we still need to detect the actual faults and defects on them, if there are any. And we want to do this because it's an important step to automate the hull condition assessment. And this will definitely help the surveyor to, for the decision making. But unfortunately, there is very limited publicly available data for this, so it can be challenging to train models. But to overcome this, we actually made the first large-scale data sets for underwater ship inspection. And it includes 10 object categories with 6 ship parts and 4 faults. And they were selected based on reviews with domain experts and reviewers and surveyors and societies, so that we know for sure what they are typically looking for, that can only extract the important information. So for example, for the ship parts, we will look at propellers, anodes, CHS gratings, and overboard valves. And for faults, the main categories are corrosion, rain growth, and defects. So here we have just a few examples of how the data look like. So I forgot to mention, it's actually a data set made for semantic segmentation. So there is dense labeling, but it can also be used for image classification. So, for example, on the top row, you can see examples of chest gratings with, in this case, white mask on top of the image. But perhaps the one that is the most clear here is the propeller, looking at the purple mask on top of the image. And so for each class, we have masks like this. So it's great to have a data set, but we need to make sure that we can actually use it to train models to actually recognize the defects. So we just use a bunch of state-of-the-art models, and we first check if all the models were able to converge, which was the case. But that's not enough to really say the dataset is good or not for models. So then we use the same models, and we train them and measure the popular metrics for semantic segmentations, which are RUU and FN score, and we could observe that they could reach high accuracy. But in practice, we don't want best model. We want to find the best trade-off between time efficiency and prediction accuracy, because as soon as we get the results, if possible in real time, as soon the surveyor can actually make a decision, potentially reduce downtime of ships or make quicker the process of inspections. So then here is like a quick example during a typical inspection. So up to now, we have accumulated quite a lot of data that can be used for many different applications. But what do we do with this data? How can we use it to actually help the surveyor? So the idea now is to find the appropriate way to aggregate all this data and potentially generate reports that can be used by surveyors. And we also want always to comply with the international regulations so that the solution that we propose can be used in practice. So for this, we identified 3 different types of data, which is actually quite often also used in the guidelines for ship inspections. We first have navigation data, which correspond to where is the ROV, how is it moving, its path, and so on. We have the scene data, which is, in a way, what is the data observing and the different models. And finally, the inspection aiding data, which would support the decision, the final decision of the operator. So, for example, if there is an actual fault. So this is then the very last step of the operation. When the ROV is back on board, we generate these kind of status reports, depending on all the points of interest that the surveyors are looking for. So as soon as the semantic segmentation model detects a ship path, it kind of creates a landmark, the data sets, so that then specific status report can be generated at the specific location. So if you look at the first row here, for example, it's corresponding to a beach keel. So the first image, the first column is an image without any processing to provide context about where was this data collected and in what condition. The second column is this time using the stream of data, but as long as the point of interest was detected. So 3D, performing a 3D model of this point of interest. The third column is this time applying the semantic segmentation masks so that you can understand in one quick look if there are faults on it. So in this case, in blue, we have the hull. In yellow, it's the beach keel. In green, the marine growth. And the last column, it's a bit more descriptive to really have some values in. So it's really about spelling out what has been observed for the sequence. And very similarly, at the bottom, we can see a status report of the propeller. So to conclude, at the beginning, we had these 4 objectives. The first one, which was about making sure that the vehicle can adapt to the shape of the hull and navigate along it, regardless of its shape and size. And for this, we have sonar-based guidance strategy to enable to fully visually cover the hull. The second one was about detecting the actual point of interest in faults. And for this, thanks to the help of different domain experts and facilities, we were able to propose a new data set. After this, we also wanted to model the different ship parts to provide some better understanding of scale. And for this, we proposed a way to combine sonar data and monocular camera. And finally, it was also about creating this global solution that can be used in practice by surveyors to better and more efficiently report, document, and monitor the inspection. So the very last conclusions. I think this really contributes to the progress towards end-to-end autonomous inspections, but also thanks to the extensive testing that was done during my PhD, we were able to kind of prove the potential of such end-to-end tasks because we were able to collaborate with actual surveyors that were sitting literally next to me during the operations. So this was very valuable, and we were able then to have feedback about how in practice it's actually done. And so, but we still believe that such end-to-end tasks need to be more explored, and there's a lot of room for improvements, of course. So, for example, I believe that semantic SLAM be very valuable in the context of inspection, especially because it helps for mission management, scene understanding, and more constraints mapping. But also very importantly is specifically about the sensors, being able to handle tilting or turning perception sensor would really help achieving better coverage and more quickly, because this would also overcome the motion constraints that some vehicle might have. And finally, of course, collaborative missions are definitely relevant for fast-paced inspections. So, yes, thank you very much.
Thank you, Alex, for a great talk. Do we have any questions in the room or online, please? Well, I can see Stefan has his hand up. Steph, do you want to unmute yourself and speak?
Actually, I was just doing a little clappy icon thing, but I can maybe start questions off. So, you know, that sort of combination between sonar and visual data is particularly challenging underwater when you've got you know, turbidity and the like. So what are the most significant challenges that you came across in the work that you're doing in sort of combining those modalities, and what are your thoughts on ways forward?
Yeah, so definitely the water clarity is the biggest challenge, but that's why I think when we combine with the sonar, it's especially relevant, because the sonar is not affected by the water quality. So if we find a way to extract just enough points from the images, from the camera images, then the remaining acoustic points are actually enough to provide accurate and robust results. But finding a way to improve the images as the operation is happening would definitely help provide more insights and more relevant information than for the fusion, but also for other tasks for inspection.
Thanks.
Yeah, thanks, Alex. Awesome presentation. I have a question. So with you've got this kind of template lawnmower pattern, and then it kind of tracks more accurately the shape of the hull using sonar feedback, right? I'm curious about, I guess, you could say robustness or resilience to this. If your template had a lawnmower pattern that was kind of too deep for the size of the hull, and you kind of went off the bottom of the hull and then lost track of the hull, and you're just in kind of open water, what would it do? Is it resilient to that? Can it kind
Yes,
of regain
so-
track? Or?
Actually, when we tested, this was an issue
Mhm.
that we had multiple times. So the idea is that as soon as we lose track of the hull, then we would come back to the last place where we had the hull envisioned.
Mhm.
And so then based on this, we would update the path. But this came only quite late in the PhD. So for the majority of the project, we just made sure never to go too deep.
Right.
But,
And to navigate back to where you are, that's just based on like IMU dead reckoning or something? You don't have any extrinsic navigation
well, I mean,
information there?
we keep track of the vehicle's position.
Mhm.
So let's say we are 3 meters deep, we still are able to track the hull. But as soon as we get to 4 meters, for example, we lose track,
Yeah.
and we just come back to 3 meters and continue from there.
Okay, okay.
I think that's some. So continuing with what Ian said, I think it's an interesting problem to see in the case. Might be not of great interest, but like the moving hull of the robustness of the motion planning algorithm. When, for example, the patient pool, I don't know if we can assume the ideal conditions inside the pool, or in general, when we expect with inspection procedure, I guess we can have a pool with no wave at all. So I don't know.
Yeah. So
The
actually,
moving hull is a very interesting problem.
we actually tested quite a lot in harbors, so we didn't have like so much waves and moving ships, because this is planned to like really work in harbors. So we did experience a bit of movement from the ship, but it was not big enough to impact the system. The only impact would be if we have very small vessels, then in that case, all waves would amplify the motion of the vessel. And for these specific cases, we would just add more like safety constraints more than really robustness of the solution. So we didn't really take into account this kind of.
Any other questions from the room or from online?
With your sonar, do you find that if the hull is badly overgrown with plant life, do you lose returns? Because that would absorb a lot of the sonar things.
Surprisingly, we were still able to recover most of the data, but of course, it's amplify the noise conditions. But because we have, I think, about 500 beams, we always have enough data to predict the sign. But this would become an issue if we have only a few beams. Yeah.
Thanks for the talk. I kind of had a question about the way you were combining the scale you were getting from the sonar with the reconstructed point cloud. So from my understanding, you were scaling it every frame because it seemed that you were able to feed your scale back.
We actually obtain new measurements every frame. And so we build a data set over time that has like scale values for each of the different match. And then from this data set, we obtain one specific scale, which is then applied to obtain this kind of trajectory.
So this process is like offline or like
No, this is
you
online. But it's like, the thing is, maybe the first few streams it won't be so stable. But then because the idea is to converge towards one, which means that we have like a stable scale, then it actually doesn't really change, except when we have a strong change in the sea.
Okay. All right. Thank you.
I have another question. When you showed the semantic segmentation results, when the actual video, this one. So obviously, like underwater is very challenging environment, and probably more challenging than most scenarios where semantic segmentation is used, right? And I noticed you do get, it looks like you're doing just frame by frame semantic segmentation. So you got kind of flickering of things change their semantic label one frame to the next quite a lot. I wonder if you've thought about something which is kind of over time accumulating information in the linked with the SLAM solution and able to kind of stabilize the semantic labeling here.
Part of the project, not part of my PhD, but then there was master thesis working on this, where the idea would be to use frames one after the other so that you can propagate the mast and have this kind of stability. This actually quite good performance. Because maybe one thing that I can mention with this data set is actually most of the images were collected in Norwegian seas, which means that, for example, if we go to maybe even the water here, it wouldn't work as well if we don't add some of the images from the water here. So this is also maybe one of the issues with these data sets, but we still think that it's like a good base that everyone can use, extend.
So we should add to the data set through ARIAM, right? That's what I'm saying.
Maybe.
All right, unless there's any other questions, then let's please.
Can I have one more question? Sorry. Sorry to sort of jump in, but Alex, so a lot of what you talked about, I guess, is mapping. Was there much work done in the broader project that connected this through to intervention, where you're starting to do some kind of task on the hull, whether it might be cleaning or painting or sort of non-destructive testing type things, where you're actually then trying to close the loop and getting the robot to do something around the structure?
So yes, actually, it was not really part of my PhD, but as like extra in a way. We are actually investigating the way we could put like some kind of probe on the underwater vehicle to do some entities. So the idea would be to using this data set when we locate the relevant places where we would need to do some entities, then the vehicle would approach and perform some tests. But it's also because this project is actually part of a bigger European project, we had this collaboration with other fleets of robots, including magnetic rollers that would navigate on the hull. So typically what would happen is that the underwater vehicle would kind of find the point of interest, that then the crawler would reach this point, perform the testing, and potentially some maintenance tasks.
Great, thanks.
Thank you very much, Alex. Unless there's any final questions, should we please thank the speaker again?